So let's take a look at a quick example. And in order to see how boundary conditions works, the best thing is to create a very simple model and to look at the code which is actually generated by the designer mode. That's the simplest way I found to really understand the way everything works. So let's start with a new project in the designer mode of OnScale. I'll call that BC example 2 because I already made one before. And this will be mechanical dynamic 2D model. And let's choose a model in millimeter unit. So I'll go rather fast because I suppose that you know already how to do this kind of modeling. So first thing to do is to go into material, add some steel. So what I'll do is a propagation of a wave into a steel plate with a hole. And then I'll show you how to assign some custom constraint. So let's add a steel material here. So there will be no piezoelectric, so the polarity here is not important, and I don't need piezo material. Okay, let's add a forcing function. So I'll use Rico wavelet, 1 megahertz. Okay, and let's create some primitives for the geometry, right? So let's create a rectangle first. Let's edit, let's assign a steel material. Let's edit the dimension of this. So dimension will be 100 millimeter in Y direction, and it will be 150 in X dimension. Let's reset the view. So I have now a plate like this. And what I want to do is to make a hole here on the top. So let's add another rectangle on top of that and assign a void material to that. So basically I'm creating a hole on top of it. And let's move that in the right position. So the X should go from 50 to 100 and the Y should go from 80 to 100. Let's have a look. Yeah, that's okay. So you see that's how it works in OnScale. You have a precedence. So this is precedence 0, this is precedence 1, and because this has been constructed afterwards and it has a precedence 1, it basically builds on the top of the previous layer. So the material that will be used after that at the end will be steel and nothing in here. So it's equivalent as a void. Okay, so what I want to do is to assign a pressure here, which moves dynamically with the time distribution of Rico wavelet, and which goes up and travels up to this point. And I want to make this part absorb the wave, but not this part. So those two will reflect the wave, and this part will absorb the wave. And this gives me the chance to show you different types of boundary conditions that OnScale has. So the side boundaries are called a domain boundary. So if I click on that, you see that I have, because it's 2D, so I have the 4 sides of my model, Y min, Y max, X min, and X max. And by default, those are all set up to 3. So I could change that and set up like a symmetry, absorbing, fixed, impedance, or periodic. But in this case, I will really change all the edge. And you see that here, I only want to catch this part, not the whole edge. So I'll basically leave all of that to free. And what I have to do instead is to click on constraint here and to add a constraint which will exactly be defined here at this position. So this will be an absorbing boundary condition. And the Y here it's at 80 millimeter, so it should be the same 80. And the X should go from 50 to 150. Okay, to 100, sorry. Okay, now you see I have my boundary condition here, my absorbing boundary condition. And now I need to assign the load. So I'll basically go here and select. So there are 2 ways to assign loads by edge, by selecting the edge, or by geometry interface. And this is also because in the code you have several ways to assign. And I'll choose the steel primitive, and I'll assign that to the bottom of side tree, right? So this will be pressure load with the time function. So this is the time function, the Rusu wave that I created before. There will be an amplitude factor of 10, which is fine here. Okay. Now let's check a bit the mesh size, because it won't necessarily be the right mesh size. And yeah, if I look at this, well, by experience, I know this is too coarse. So I can go into mesh, go in configuration, and you'll have basically basic, wavelength base, and define. So if I select wavelength base 15, which is basically what is recommended, this is slightly too small, I think. So, well, I could use that, but this will take more time to calculate. And I found out that by using 7, half of it, I'll still have an acceptable quality and good speed. So I'll just use this one, 7. Okay, and then let's go. So for the analysis, I need to set up the simulation time. So also by experience, I think the right simulation time here would be, let's say 50 microseconds. And what kind of output do I want? I want two kinds of output. One will be acoustic pressure, let's say at the middle, in order to just to get an idea. Because my wave will travel here, and because it will not reflect, it will be absorbed. I shouldn't see any pressure coming back, right? So we'll see if I can see that in the signal. And then I can go here and select a snapshot of the acoustic pressure as well. Now, when I will run that on the local, I could run that on the cloud as well, but I'll just run that on local so you can see more easily what's happening. And let's choose time history. Okay, like that. Array acoustic pressure. Okay, and let's save that and ready to run this. Let's run and see if everything is fine. So here it is. It starts to calculate. I can see my wave here moving. And as you can see, the wave goes to that point, and yeah, it is absorbed here. It is not reflected. You see that those two sides are reflected. This side is not reflected. And the probe that I placed here is giving me this kind of signal. So we see that here, reflected signal is just because of those two sides, right? So you see we have an influence of those two sides. So I have a very weak signal coming back here. Okay, so this model is okay, it's working. And now what I really want to do is to show you what kind of code this kind of study has generated automatically. So I'll just open the generated code in the analyst mode. So to show you the analyst code that has been generated, I just opened the folder in which the calculated files are located, and you see that this is the designer mode, the GFP format, and the FLX INP, like input file, will be the analyst code generated by this. So if I double click on that, it will open OnScale Analyst mode, and I'll be able to look at the code of the simulation example that I was looking. So if I go quickly over this code, the beginning has just a bunch of variables that have been defined, like the frequency, the parameters of the domain size. Those are the key points and the mesh definition stuff, the geom comment. So I've been detailing all of that in the previous video of the series, so this shouldn't be a surprise for you. You should understand all this. This is the drive function, the Rico wavelet. And if I go down, this is the material properties. So I have only one material, which is the steel. And this is the site, the assignment of the material to the geometry using the block primitives. And here are the boundary conditions. So that's the interesting part on this in this situation. So we can look at the four bound side, which are basically set up to 3. So those are the global boundary on all the sides of the model. And if I wanted to set that to absorb, well, it would be really simple, just ABSR, and I would get absorb. Now, let's look at this part here, which actually show you how to define the other part, the edge that I selected. So the code is actually this, and those are just the definition of a bunch of variables that are useful for this. Why? Because so there is a definition which basically gives a name to this constraint. So it's called constraint 1, and this is the type of boundary condition. So it is an absorb ABSR boundary condition. And here is the selection of the nodes which corresponds to this edge. So if I show you again, the designer mode, this is this edge here, right? So in practice, this is defined by the following key points, and those key points I can actually go, because I run that. So yeah, I would have to run that in Analyst to actually see the variables in here. So, well, I could do it actually, because that's also interesting. So I'm just rerunning the same stuff, but in Analyst this time. So I'll be able to see what those parameters are equal to. So, and you see that as soon as I launch the solver, those variables appear here. So it's exactly the same simulation, right, that I just ran before, but this time I'm able to see those results here. So I don't actually need to look at that again. I could just kill that because I already show you up to the end. And now I have a visualization of the value of those variables. So those key points here, IS, IE, JS, G, so we can see what they correspond to. So IS is 60 and IE is 120. So why those values? Why do I have 60 and why do I have 120? And JS and JE are actually exactly the same value. It's 96. Well, this refers to the number of the element which is actually located at this position. So if you see this this edge here selected, if I zoom on that, the element which is exactly here is the element 60, and the element which is here is the element 120, and this column is here is the element number 96 in the y direction. So that's why those are equal to those values. Now, you could say, okay, but how do I know the value of those key points? Well, several ways. You either are fully working with Analyst mode and then you define yourself manually those key points, so you know what is the value of the key points. Or if you worked in Designer, you will see this kind of code here. And this code here has been used to actually determine the value of this. What this code is doing is that it's defining the geometry dimensions. So here you see bxmin is going from 0.05 to bx max 0.1, and here I'm using so the same for ymin and ymax, and I'm using this function called CLS node, which will give me the corresponding node corresponding to the position of this this node. So this function is very useful. So this is the input, the function is here on the right, and this is the output. So those value, i.e. je, will become equal to the number of the node, equal to this the position that I define here. And this is how i.e., je, is, and js are calculated, and the constraint here and the node comment here is selecting this range of nodes. So you see that all this code here is used to actually select this range of nodes. So that's how the boundary conditions are selected manually. So you can go a bit down to show you the rest of the code. So there is a calc which tells me that I want to calculate the acoustic pressure. There is a plot that I'll talk about plot right after, which is the pressure load. So this is the dynamic pressure load. So you have the definition of the plot, which takes the name of, so I give it a name, which is called load1. I give it a function dependent of time. So this is the forcing function, the recurve wavelet that I define. I give it direction. So in this case, the direction is defined according to the material steel out direction. So it takes the material steel and the out direction of it. And the SDF2 command is taking the name of this load, is taking the vector created here, and it's taking the material, and it's taking the side, so the actual side of the material to which the pressure will be applied. So all of this will define the pressure load dependent on time. After that, I have a bunch of graph functions which will allow me to actually display the model. And I have the part command, which will help me to display the time history curves. So I see that here I'm asking for the acoustic pressure at this specific location, y and x and y, which is defined here. And I'm also outputting the drive function that I define. This is the part where actually this is calculated. So in this part here, you have the definition of the time step and the total simulation time. You see that the 50 microseconds that I define are equivalent to the t time parameter variable. Then I divide that by a certain number of steps, which gives me an exec, which is divided in loops. And the loops basically are useful because I'm defining here proc, which is basically a function which has the name plot. And this loop here will plot the data at each time step. And here I'm running this function. Proc plot means I'm running this function that I created before, and loops time. So it's a certain number of time which corresponds to the end loops parameter, so 20 times. And within this function, I'm executing a certain number of time steps. So this is why this is the total number of time steps performed for the simulation. So let's suppose that I have 1,000 time steps in total, but in those 1,000 time steps, I only want to output 20 times the update of the data. I don't want to output 1,000 times the data because it would be too much. My files would be too big. So I'm just choosing to put that into a loop and to execute that 20 times. That's basically what it means. And this is the data output. So this is basically the data are saved into an FLX data file. And that's it. That's it for this example.